Okay, I'm going to lecture through the study guide for Module 11. I'm going to try to go straight through, even though you really only need to watch half for the snow day. The other half is just for team-packed people, or in case the lab takes a really long time, then everyone can watch it after the next class before they take Module 11 test. So, question 1 says, name the 4 fundamental forces in creation. So that would be the gravitational force, the electromagnetic force, the weak nuclear force, and the strong nuclear force. Or you could say that there are really 3, that the weak force and the electromagnetic force are one and the same. And number 2, I hope I have the same paper as everybody. I know that's a problem sometimes. Which is the weakest of the fundamental forces? That's gravity. Can't even overcome friction. And which is the strongest? The strong nuclear force is the strongest, which is obvious because trying to keep a bunch of positively charged protons in a nucleus, which all want to repel each other, because they're all the same charge, takes a lot of force. Like, the amount of force holding a nucleus together is just unbelievable. Question 3. Name the 3 principles of Newton's universal law of gravitation. All objects that have mass have a gravitational attraction to every other object with mass. The second one, gravitational force is directly proportional to the mass of the objects that you're considering. So that's basically saying if you increase the mass of the objects, the gravity between them will increase, directly proportional. The third one says that gravitational force is inversely proportional to the square of the distance between the objects. So when you have 2 things that are 1 distance apart, if they get further apart, distance is increased, that means gravitational force has decreased, because they're inversely proportional. If distance goes up, gravity goes down. If distance goes down, gets closer, things get closer, gravity goes up. Inversely proportional. Question 4. Oh, it's a math problem. Okay, so we'll have a look with the chalkboard here. I got new chalk. The gravitational force between 2 objects, one has a mass of 10 kilograms, the other a mass of 6 kilograms, is measured when the objects are 10 centimeters apart. If the 10 kilogram mass is replaced with a 20 kilogram mass, so that's kind of the first place we need to start considering. I don't know why there's a string around this. Okay. It's a 10 kilogram mass, so we'll write our equation first. Okay, so we know that the gravitational force is directly proportional to the masses, and it's inversely proportional to the square of the distance, and I told you before there are other factors to consider, but we're just finding how gravitational force changes so we don't have to worry about the other things in the equation. So this says the 10 kilogram mass is replaced with a 20 kilogram mass. So the change in mass 1 is going to be, it goes from a 10 kilogram mass, what do you multiply it by, that factor of change, to get the new mass of 20 kilograms? Well, 10 times 2 is 20, so our factor of change is going to be 2. The change in mass 2, it says mass 2 started at 6 kilograms, and it's replaced with a 12 kilogram mass. So we have to figure out what the factor of change is. 6 times what gives you 12? Well, once again, it's 2. 6 times 2 gives you 12. The factor of change in mass 2 is also 2. Does the distance change in this one? They're 10 centimeters apart, and it doesn't appear that it does. So then we don't have to worry about distance. So we just plug in the changes here. The change in mass 1 is 2. The change in mass 2 is 2. There's no change in the distance, so it changed by a factor of 1. When you multiply something by 1, nothing happens, right? So it looks like the overall change in gravity is that it increases by 4 times. So your answer to number 4 here would be gravity increases by a factor of 4, or it gets 4 times bigger. Problem number 5 says this. The gravitational force between 2 objects, one has a mass of 10 kilograms, the other a mass of 6 kilograms, is measured when they're 10 centimeters apart. If the distance is increased to 40 centimeters, how does the new gravitational attraction compare to the first? So the masses in this problem don't change, so only the distance changes. And we see the distance starts out at 10 centimeters, by what factor does it change when it increases to 40 centimeters? Well, we know 10 times 4 is 40. So the factor of change here is 4. It gets 4 times bigger, right? So then we just plug that in. We know the masses don't change, or we could say they change by a factor of 1. When you multiply something by 1, it doesn't change, right? Then we know distance increases by 4 times, and we know we have to square our distance. So what's 4 squared? 4 squared is 4 times 4. 4 times 4 is 16. So the force equals 1/16 of what it used to be. So when you increase the distance by 4 times, you decrease the force by 16 times. Or you could say the force is 1/16 of what it used to be. Oh, hold on. Here's the cuteness. Lovely. Are you supposed to go upstairs?
Uh-huh.
Go.
What is Mom? Yes.
I know. Go find Granddad. He told you to go. Where'd he go? Oh, let's go see. Let's see. So that's problem 5. The gravitational force is cut into 16ths, or it decreases by a factor of 16, or you could say, I guess I would just say the gravitational force decreases by a factor of 16, because the 16's in the denominator, so that means the force is decreasing. That's problem 5. I need to get this board a little cleaner. Okay. Number 6 says this. The gravitational force between 2 objects, the first has a mass of 1 kilogram, the second a mass of 2 kilograms, is measured when they're 12 centimeters apart. The 1 kilogram mass is replaced by a 5 kilogram mass. So, why do I use chalk so much? So the first mass with a 1 kilogram mass, you multiply it by something, it becomes a 5 kilogram mass. Well, the factor of change there is 5. 1 times 5 is 5. The second mass, it was a 2 kilogram mass, and then it changes and becomes a 4 kilogram mass. So it had to change by a factor of 2. This 2 times 2 is 4. Then it looks like, oh, also the distance is changed. So the distance was 12 centimeters, and then it has a factor of change, and it ends up being 4 centimeters at the end. So 12 times what gives you 4? Well, 12 divided by 3 is 4, or 12 times 1/3 is 4, right? So the factor of change there is 1/3. The distance was cut by 1/3. And then we just plug in. So we plug in the factors of change. So force is going to be 5 times 2 in the numerator, right? Because the mass changes by 5, that mass changes by 2. And then both masses increase. The distance changes by 1/3, and distance has to be squared. So then we get 10 in the numerator, and we get 1/3 squared, which is really 1/3 times 1/3, which is 1/9, because 3 times 3 is 9. So we get 1/9 in the denominator. Okay? So then we just have to kind of figure out what that means. Well, what that means is, I wish I had more space. Hold on. When we do fractions like this, remember 10 divided by 1/9 really equals 10 times 9/1. Because to divide by a fraction means you multiply by the inverse of the fraction. So 10 times 9/1 is really 10 times 9. So 10 divided by 1/9 is actually 90. So when I get the answer of 90, that means that the gravitational force has increased by 90 times. That's a really big number. So then I want to think through, have I done this correctly? So when mass changes by factors like this, mass and force are directly proportional. So when mass goes up by these factors, force goes up. Force goes up, that's good. When distance goes down, force goes up because they're inversely related. So distance went down, force went up. In all cases, that would make force go up. Technical difficulty. Uh-oh. Okay, hopefully it's still working. So all of these things would make force go up. Cumulatively, they make force go up by 90 times. So the gravitational force increases by 90 times in this problem. Make sure that you're good with fractions. You feel comfortable with it. I don't know if Dr. Weil does the math a little bit differently when he gives example problems than I do. This is just how I think about it. So if that works for you, great. If his way works for you, great. If you work with fractions another way, as long as you're doing the math in a valid way, great. It doesn't have to be exactly my style, but that's how I think about fractions. Okay, so that was problem 6. Let's see. Keep my equation up just in case we need it. Okay, so problem 7. I have chalk dust all over me. I forget what it's like now that we have dry erase boards. Oh, just a moment.
Can you have some money?
Stop. Hold on. Did you go